How do you do? My name is John Harrison, and I'm the Managing Director of TecEco Pty Limited. I'm going to talk to you about a solution to the global warming problem. All previous solutions that have been suggested can't make money, whereas this one can, and so it will succeed. Please ask your friends to also watch this video, as it will take a certain amount of financing and people power to make it happen. Thank you. Gaia Engineering and the new TecEco NMG process to profitably sequester massive tonnages of CO2 in the built environment as synthetic carbonate concretes represent a solution to global warming. On TV a couple of days ago, a CSIRO scientist said that the 2012 anthropogenic emissions for CO2 were 36 billion tonnes. In an article published in Nature last year, 33 billion tonnes was the figure mentioned. There's been a huge increase. Portland cement is a major contributor, according to the Chinese, at 8.8%. Geosequestration is not going to solve the problem. There are legacy issues, and leakage will eventually catch up with it. It's downright dangerous. The Earth's crust is just not stable enough. I realize that the answer to the world's problems lay in an industrial ecology that utilized wastes like CO2 and bitters, desal wastewater, or oil process water to create valuable products for the world's biggest market, which is building and construction. By including the manufacture of not only our patented carbonating cements, but aggregates in the concept of the synthetic built environment, a solution to global warming can be achieved. TecEco have changed the technical paradigm in favour of making CO2 and other waste resources. I've been at this for a long time. In 2002, Fred Pearce, writing for New Scientist, said, "There is a way to make our city streets as green as the Amazon rainforest. All we need to do is change the way we make cement." Now, he was talking about our eco-cements, but since then I've realised that if we include synthetic carbonate aggregate and consider concrete as a whole, the sequestration potential is absolutely enormous. Just look at the blue line on this graph. For 2011, the sequestration is potentially about 23 billion tonnes. That's about 2/3 of total anthropogenic emissions in that year. In my opinion, a viable sequestration technology must be simple, scalable, have low upfront capital costs, low environmental impacts, produce saleable product with insatiable markets, and be easily implemented and deployable over a wide geographic area. It should also ideally be industrially symbiotic and address one or more other major problems facing the planet today. Gaia Engineering satisfies all the criteria in the previous slide, and it is a magnificent example of industrial ecology in action. It can utilize many waste streams, and nothing is produced that cannot be utilized. It is the only potentially profitable solution. There are environmental advantages, not impacts. The process is scalable and can use intermittent energy from non-fossil fuel sources. It can add value using the energy available without having to store it. Gaia Engineering can produce synthetic carbonate concrete and building products with it. The built environment represents what we do on this planet, and it is a large, insatiable market for synthetic carbonate building products at the right price. Gaia Engineering addresses other problems such as waste utilization and the production of cleaner water. Gaia Engineering has much lower costs than older processes, such as that developed by Nettle some years ago, because there are less process steps. Gaia Engineering involves no mining, no transport, no grinding, and no need to process silicate. No wastes are produced that cannot be utilized or recycled. The output from the process is saleable. Over the last 4 billion years, CO2 produced by animals, volcanoes, and other sources has been sequestered in carbonate sediments like limestone. Over 40 billion gigatons. That's a lot. And it's permanent sequestration. There's a choice of two cations, calcium and magnesium. Both are feasible. We plan to use magnesium because of the low molecular weight. It's ideal for scrubbing CO2 out of the air and sequestering the gas into the built environment. More CO2 is captured using magnesium than using calcium, as the figures in this slide demonstrate. At 2.09% of the crust, magnesium is the 8th most abundant element. If we run out of desal wastewater and oil processed water and other waste sources, we can always use seawater, because every litre contains 1.29 grams of magnesium. There are a lot of hydrated magnesium carbonates to choose from. We're going to be utilising nesquihonite, and the reason is the microstructure. Nesquihonite has an ideal shape that contributes strength to a composite like concrete. It can be manufactured easily using our NMG sub-process at room temperature with little energy. It can be used directly in products such as acoustic panels, non-structural panels, insulation, etc. Nesquihonite is stable over a wide PT range. It changes with heat to magnesite, which is even more stable. It's a source input for the manufacture of reactive magnesia used in our cements, and we also plan to use it to make our synthetic carbonate and waste aggregate. Our colleagues at the University of Rome have a batch process for producing nesquihonite from brines. What we're doing at the moment is developing a continuous automated process. And we're also developing our tech kiln, which is essential for making the magnesium oxide binder we plan to use. There's a case for synthetic aggregate. Sand and stone aggregates are in short supply in some areas, and nesquihonite is an ideal mineral for the manufacture of reactive magnesium oxide, our binder, as well as synthetic carbonate. Reactive magnesium oxide to magnesium hydroxide to magnesium carbonate has high molar volume growth, more for less. It has ideal microstructure. It's stable, low pH, and it creates polar bonds in composites, making it ideal for binding wastes. Most importantly, nesquihonite sequesters significant amounts of CO2. This poster depicts the concept of the process. CO2 from the air combining with calcium and magnesium cations, producing the built environment. This flow diagram shows oil processed water, desal wastewater in our NMG process, producing magnesium carbonate for aggregate and other building components, and also as a feedstock to our kiln. The reactive magnesia produced in the kiln makes our cements, along with a little Portland cement and perhaps some other wastes like fly ash and blast furnace slag. The process uses a considerable amount of industrial CO2. The big picture is demonstrated in this vector diagram. There are sub-processes that can be included, like the tech reactor process for sequestering even more CO2. There's a route to energy, but what we're going to be looking at in more detail is this circular industrial ecology here. The NMG process produces nesquihonite for our synthetic carbonate aggregates and other components. It's also a feedstock to our kiln to produce magnesium oxide used in our cements. The emissions, along with other point source emissions, go back into the process, combined with an alkali metal cation, in our case magnesium, to produce more nesquihonite. Consider the thermodynamic cycles involved. At the moment, our eco cements cannot be made with capture, and so even though they sequester the chemical release during manufacture, there are some emissions associated with the process energies. The NMG process has capture during manufacture. It uses a man-made nesquihonite input in which there's capture, and there's capture during setting. That's 3 stages of capture. The sequestration potential is enormous. It's shown in this diagram. Stage 1, the NMG process. Stage 2, the TecEco kiln, calcination. Stage 3, our eco cements bonding together synthetic carbonate aggregates to create carbonate concrete. In stage 1, the production of nesquihonite, the sequestration is 1.084 kilograms of CO2 per kilogram of nesquihonite produced. The kiln has net emissions of 0.382 kilograms of CO2 per kilogram of magnesium oxide produced, and the reabsorption of CO2 by our cements, the stoichiometric amount of sequestration occurs at 1.092 kilograms of CO2 per kilogram of magnesium oxide. In total, that's about 1.75 kilograms of CO2e per kilogram of magnesium eco-cement. The production of synthetic carbonate aggregates using nesquihonite only involves step 1, so we're looking at 1.084 kilograms of CO2 per kilogram of synthetic magnesium carbonate. Very like the solvate process, occurs rapidly at a relatively low pH. The reactions you can look at later, but importantly ammonia is recycled in the process. Ammonia is our pH adjuster. Our new tech kiln is an important part of Gaia Engineering. It will operate in a closed system and therefore will not release CO2 to the atmosphere. Instead, it will be recycled to the NMG process. The kiln can be powered by various, potentially cheaper, non-fossil fuel sources of energy, such as intermittent solar or wind energy, and it's energy smart. It can be powered up or down depending on the energy available. It will grind and calcine at the same time, and therefore run 25 to 30% more efficiently, and it will produce more precisely defined product. It operates at relatively low temperatures, lending it to the use of solar power directly or waste energy. Gaia Engineering is an example of a geometric industrial symbiosis. In this diagram it's shown interfacing with the nicromet process, in which nickel and cobalt are produced from lateritic ores. These cliffs behind me are made of limestone. Limestone and other carbonates represent about 8% of the crust. Every litre of seawater contains 1.2 to 3 grams of magnesium and about 0.4 grams of calcium. That's enough to last basically forever. What we need to do to survive is build our homes like these seashells using CO2 and alkali metal cations. This is geomimicry. Gaia Engineering can balance the carbon cycle. We need to biomimic plants and algae by building our cities so they absorb CO2. In this way, we can survive the future. My company TecEco at this point in time have patents granted and patents pending. We've managed to survive what in Moore's innovation curve is referred to as the chasm. We're now looking to develop our technology. Contact details are shown in this slide.